So in this lecture, we are going to talk about the carbonyl compounds. So carbonyl compound contain the carbonyl functional group, so which is very important functional group in the organic chemistry. We can form various kind of organic products from these carbonyl compounds. So this there are two type of carbonyl compounds. We can classify this carbonyl compound into two types, that is aldehyde and ketone. So aldehyde contain this CHO functional group and ketone contain this CO functional group. So we can see that in case of aldehyde there is free hydrogen, but in case of ketone there is no free hydrogen. So based on that, based on this difference, we'll see that this ketone and aldehyde show some different properties. We'll see that later. So basically this aldehyde and ketones are used as reagents, solvent and constituent of various fabric, plastics and drugs. If we see for the carbonyl functional group, the both carbon and oxygen are sp2 hybridized. You can see the sp2 hybridization. So this bond angle is here 120 degree. So due to difference in electronegativity between the carbonyl carbon and oxygen, there will be generation of dipole. And we can see that in case of the carbonyl compound, we know there is dipole-dipole interaction. And because of this dipole-dipole interaction, they are basically combining with each other. Different carbonyl compounds combining with each other. So because of this dipole-dipole interaction, their boiling point is greater than the normal nonpolar hydrocarbon. Now we are going to study the various kind of method of preparation of aldehyde and ketones. So first one is from alcohol. So from alcohol we can easily produce ketone, carbonyl compounds, ketone or aldehyde. So let's see. So this is a 1 degree alcohol. So if we oxidize this alcohol, we'll get aldehyde. 1 degree alcohol, after the oxidation will give aldehyde. You can see that there is free hydrogen. So that is basically aldehyde. So what is the oxidizing agent we have to use? The oxidizing agent we have to use here PCC. PCC is basically pyridinium chlorochromate. You can use other oxidizing agent, but this is very good, one of the good oxidizing agent. So PCC produce this aldehyde from 1 degree alcohol. So if we see the mechanism, so on the first step, the lone pair of the oxygen of the OH group first attack this chromium and this CrCl bond breaks. On the next step, we can see there is a deprotonation is happening, and next step CH bond breaks, and that will form the C double bond O, and that is the product. Simple mechanism. I hope you understand the mechanism. So from the 1 degree alcohol, we are getting aldehyde via oxidation. So we are getting aldehyde from 1 degree alcohol via PCC. You can also use a Jones reagent for the oxidation of 2 degree alcohol, or you can also use PCC for the oxidation of 2 degree alcohol. So if we oxidize the 2 degree alcohol, so this will produce ketone. The mechanism is similar, but in presence of PCC, this 3 degree alcohol will not give any kind of product. This is the 3 degree alcohol. So it will not give any kind of product in presence of PCC. So in presence of copper at 300 degree centigrade temperature, 1 degree and 2 degree alcohol will give similarly aldehyde and ketone respectively. But in case of 3 degree alcohol, okay, the reaction is quite different. So it will produce alkene. So this alkene is basically produced via elimination reaction. Simple elimination will occur, and that will produce, water molecule will be removed and produce this alkene. So we can see that for the 3 degree alcohol we are getting the alkene, but in case of 1 degree alcohol and 2 degree alcohol we are getting the aldehyde and ketone respectively. From the hydration of alkyne we can also get the carbonyl compound. So if we do the hydration of this alkyne in presence of 1% HSO4 and 20% H2SO4 at 60 degree centigrade to 80 degree centigrade temperatures, so basically water, addition of water is happening here, so that will produce acetaldehyde. So see the mechanism. So lone pair on the oxygen of water molecule will attack this carbon, this one of the CC bond breaks, and that will produce this compound, okay, this intermediate. Then negative charge on the oxygen again attack this mercury and reproduce this cyclic structure, and this mercury carbon bond breaks. There will be generation of negative charge, and on the next step just protonation and deprotonation will occur. So in this case there is deprotonation is happening, so this proton will be abstracted by this negative charge. So this is the enol form, and after that we will see the ketonol tautomerism. So that will produce this aldehyde. So this is the mechanism of the hydration of alkyne reaction. Now what will be the product if we use this reactant PHC triple bond C CH3? So in this case, if we do the hydration reaction, so we'll get this product PHCO CH2 CH3. Why not this product? Why this product is not forming? This product is forming. Now we'll explain that. So if we break this bond, okay, one of the CC bond, if we break this CC bond, there are two possibilities that can generate this structure or this one, that is basically the positive charge on this carbon or negative charge on this carbon. Okay, so positive charge on this carbon is stable because of this plus R effect. Okay, resonance stability of the benzene ring. This is basically phenyl ring benzene ring. So this benzene ring will undergo resonance with this positive charge on this carbon atom. Okay, but in this case only see the plus I effect, and we know that the resonance stability is much more greater than the plus I effect, so this structure is less stable comparatively compared to this structure. Okay, so the mechanism will be like this. The water molecule, the oxygen lone pair on the oxygen atom of water molecule will attack this carbon, and this CC bond breaks. One of the CC bond breaks, that will generate the negative charge, and the next step protonation and deprotonation will occur, and that will produce the enol form, and after keto form will be produced. So this is the product, not this one. Okay, so you can see that if this is the structure, if this structure formed, then the product will be CH2, but this structure is not stable, that's why you are not getting the other one. Now what will be the product in this case if we use this reactant? So in this case the product will be terminal, the aldehyde. Okay, carbonyl group on the terminal position, you will get the aldehyde. Similarly, we can explain this via above method what we have discussed. So there are two possibilities. Okay, generation of this or this structure. So there will be negative charge on this carbon, and we know that Cl has a minus I effect, so this negative charge on this carbon will be easily stabilized by the minus I effect of this chlorine atom. But in this case, the negative charge is much far away from this chlorine atom, so this negative charge is not basically easily stabilized by the minus I effect of the chlorine atom. So we can say that this negative charge, so this structure is less stable. So the reaction mechanism is the water lone pair of oxygen of water molecule will attack this carbon. So one of the CC bond breaks, there will be negative charge generation, and after that protonation, similarly protonation deprotonation will occur, that will form the enol form, and after that will be tautomerized to keto form. So if we use this reactant, we'll get this aldehyde. This is the reaction mechanism. I hope you guys have understood. Next is the hydroboration of alkyne. So from the hydroboration of alkyne, we can also produce carbonyl compound. So for the hydroboration, not only the hydroboration and oxidation. So for the hydroboration oxidation, we have to use first diborane, then we have to react the product, whatever we are getting by reacting with diborane, we have to react it with the H2O2, that will produce carbonyl compound. So we just need to react it with three molecules of reactant with the pH3, that will produce this compound. After that we have to react this compound with H2O2. So oxidation is happening, that will produce this enol form, and that will be tautomerized to keto form. So if we use this reactant and if we do the hydroboration oxidation, the product will be this one. So just remember one thing, higher alkyne except terminal alkyne will give a ketone during hydroboration. Just remember this one, higher alkyne except a terminal alkyne will give a ketone during hydroboration reaction. Now in this case, what will be the product? So the carbonyl group can be on this carbon or on this carbon, so we just need to analyze it. So during the hydroboration reaction, how the reaction is basically happening, so this is the BH3, basically the hydride ion first attack the sp hybridized, one of the sp hybridized carbon. So this H minus ion, suppose this H minus ion attacking this carbon, so there will be generation of negative charge here, or if this H minus hydride ion attacking this carbon, there will be generation of negative charge here. So which we know that plus I effect of C2H5, that is ethyl group, is much more greater than the plus I effect of CH3. So the negative charge on this carbon is less stable because of the more plus I effect of this CH3 group. So the negative charge on this carbon comparatively stable. So the hydride ion will attack this carbon, there will be negative charge that will abstract this BH2. So it will be HBH2, and this will be the double bond. Next step on the oxidation, it will be OH. We know the BH2 group will be converted to OH, and this is the enol form. After that, tautomerization will occur, and that will produce this product. I hope you have understood. Next reaction. From the ozonolysis we can also produce ketone. Okay, so first step, the alkene will be reacted with ozone gas to form the monoozonide. Okay, so after this formation of monoozonide, we have to react this monoozonide with zinc water. Okay, ZnH2. So this monoozonide collapse, okay, in a cyclic manner. You can see the mechanism is happening by a cyclic manner. So this bond break. So bond making is happening. So ultimately it will produce this ketone and aldehyde. So for the trick, just remember that just break this bond and just add oxygen to the carbon. Okay, to this carbon. That will be your product in case of alkene. Okay, just break bond and add oxygen. So in this case, just break bond and add oxygen. And remember that if you use the H2O2 instead of ZnH2, the aldehyde further oxidize to acid. Okay. From Grignard reagent also we can produce carbonyl compound. So this is alkyl cyanide. So we are reacting it with methyl magnesium bromide. So we know there is del negative charge and del positive charge. Okay, del negative charge on the carbon, del positive charge on the magnesium. So this CH3 methyl group will attack this carbon, and this one of the CN bond breaks, and that will produce a negative charge, and this negative charge will abstract the electropositive MgBr that will produce this compound. So after that, lone pair on the oxygen of water molecule will attack this magnesium, and this NMG bond breaks, and that will produce this compound. Okay, this imine. So after that, water molecule attack. So simple hydration will occur in this case. This is the mechanism of hydration. So after the hydration, it will produce the carbonyl compounds. So basically ketone is forming here. Okay, so if you use the suppose hydrogen cyanide, so in that case, what will be the product? If you are reacting this hydrogen cyanide with methyl magnesium bromide, so in this case product will be CH3 CHO. From the ester we can also produce carbonyl compound. So if we react this ester with Grignard reagent, we can also produce ketone. So this is the ester, that is methyl formate. We are reacting it with methyl magnesium bromide. So first step will be addition of magnesium to the carbonyl carbon, and this CO bond, carbonyl double bond, one of the CO bond breaks, and that will produce negative charge on the oxygen. So this negative charge on the oxygen will abstract the electropositive MgBr. Okay, Mg. There will be generation of OMgBr bond. So on the next step, OMg bond breaks, and we know this OC2H5 is very good leaving group, OET minus. Okay, so it is very good leaving group. So this group leaves, and there will be generation of again carbonyl compounds. This is the aldehyde, acetaldehyde. By the distillation of calcium salt of particular acid, you can also produce carbonyl compounds. So if we distill the calcium salt of the acetic acid, so if we distill the calcium salt of acetic acid, that is calcium acetate, so we will get the acetone. Similarly, if we distill the mixture of calcium acetate and calcium formate, we'll get the mixture of these three products, that is acetone, acetaldehyde, and formaldehyde. We'll get the mixture of these three. From the Rosenman reaction, we can also produce aldehyde. So for that case, the reactant should be acid chloride. So how can we produce the acid chloride? We can react this acetic acid with thionyl chloride, so it will produce the acid chloride, or PCl5 you can use, but base product, base yield will be if you reacting this acid with the thionyl chloride, this will produce the acid chloride in greater amount. So this acid chloride need to be reacted with PdBaSO4, that is palladium barium sulfate, in presence of boiling xylene. So we basically add this BaSO4 because in presence of BaSO4, this aldehyde further cannot, the aldehyde which is produced here cannot be oxidized further. Okay, that's why we use BaSO4, barium sulfate. So acid chloride is converting to acetaldehyde in the Rosenman reaction. By the Rosenman reaction, we cannot produce formaldehyde because for the Rosenman reaction, in order to produce the formaldehyde, we have to use this reagent HCOCl, but it is very unstable at room temperature. So that's why we cannot produce formaldehyde from via Rosenman reaction. Next reaction is Stephen reaction. So in the Stephen reaction, the reagent is alkyl cyanide and SnCl2 and HCl. So in presence of SnCl2 HCl, alkyl cyanide will be reduced to RCH11NH.NaCl. So after that, simple hydrolysis will occur. So after the simple hydrolysis, it will produce carbonyl compound. Okay, it will produce the aldehyde. We can also produce aldehyde from the alkene via oxo process. So in the oxo process, we basically use the mixture of carbon monoxide and hydrogen gas at a certain amount of pressure at particular temperature. The catalyst we use here, the cobalt catalyst. So in the oxo process, we will get two different kind of aldehyde from the alkene. So one is internal, another one is terminal. We can also produce the ketone by heating the beta keto acid. So how can we produce this beta keto acid? So we can produce this beta keto acid by heating by hydrolysis of beta keto ester. We can produce this beta keto acid by hydrolysis of beta keto ester. So after the removal of carbon dioxide gas, it will produce this enol form, then it will be tautomerized to keto form. Okay. We can also produce carbonyl compound by the fetal curve acylation reaction. So in the fetal curve acylation reaction, what are the reagent we use? We use basically acid chloride and AlCl3. Suppose we are reacting this with benzene. Okay. In presence of acid chloride, okay, and Lewis acid AlCl3, so benzene will produce acetophenol. This is one of the aromatic carbonyl compound. How this reaction is happening? So what's the mechanism of this reaction? So we can see that we also know that basically the aluminium is electron deficient species because it is an Lewis acid. So the chlorine atom will give its lone pair to the electron deficient aluminium. There will be negative charge generation on the aluminium and positive charge generation on the chlorine atom. So on the next step, the lone pair on the oxygen atom will form a bond between the carbon and oxygen. So, and this C-Cl bond breaks. Okay. So there will be generation of acylium carbocation. This is the acylium carbocation. On the next step, simple electrophilic reaction will occur. So one of the double bond of benzene breaks, and this will attack this acylium carbon. Okay, so on the next step, so this will be the carbocation that generates. So on the next step, in order to get back the aromaticity, this CH bond breaks. So the final product will be the acetophenone. So in this way, we can also produce this compound that is known as benzophenone. So this is the structure of benzophenone. So in order to produce benzophenone, what we have to do? We have to react this benzene with PHCOCl in presence of AlCl3. Okay, and that will produce this compound.